endowed chair at the Electrical and Computer Engineering Department of the University of Waterloo. Where he has held various academic administrative positions since 1993. He is also the recipient of 2017 IEEE Power Energy Society Outstanding Power Engineering Educator Award, the 2016 IEEE Canada Electric Power Medal, and of multiple IEEE PES Technical Council and Committee Awards and recognitions. Dear sir, we are very happy to have you with us in this session. Also have with us the session chair, Professor Dr. S. Shahnawaz Ahmed, Professor, Department of Tripoli, Buet, and distinguished Professor, Professor Dr. Kamrul Hassan, University of Bangladesh, as the moderator. In this session, we will have 35 minutes for the keynote presentation and around 10 minutes for discussion or question and answer session. There will be a reminder after 30 minutes, just 5 minutes before the presentation is ending. May I now kindly hand over the session to Honorable Session Chair, Professor Dr. S. Shahnawaz Ahmed.
Thank you, Dr. Ratil.
Sir.
I think you already introduced famous and renowned professor, Dr. Claudio Canizares. I also know him through his work. In fact, he is also author of a book, editor of a book, Electric Energy Systems Analysis Operation, which I use as a reference in one of my courses, which I offer in Buet, Parts of Operation Control. So I think we are already behind the schedule by 25 minutes. So I would request our honorable keynote speaker, Professor Canizares, to deliver his valuable speech on overview of microgrid. I think all of you will enjoy it. Thank you.
Okay, thank you. Can you hear me?
Yes, sir, we can hear you.
Okay.
Yes, sir, we can hear you.
Thank you for the invitation. Thanks for the introduction. As already mentioned, Professor University of Waterloo, and I'm going to be focusing on an overview of microgrids. So the work that I'm going to present here, the slides I'm going to present here, is the result of the work of multiple researchers in my group, which are listed here. No time to go through all of them, but basically is reflecting the work that my group has performed or has carried out in the last few years in this area. So a brief introduction to the University of Waterloo is a university focused on engineering and science, about 150 kilometers due west from Toronto. It's basically, as I mentioned, 6 faculties. The most important ones are science, math, and engineering. And we have about 40,000 students between undergrad students, grad students, and other visitors. It's a co-program in terms of the students basically study one term and work one term. We have 2 terms a year, and we have a significant research funding. These figures might be a bit old, but we have we are one of the 10 top research universities in Canada, and I belong to multiple institutes. And I belong to the Waterloo Institute for Sustainable Energy. The engineering faculty is one of the largest, or is the largest in Canada, and in both of these departments that you can see here. And is, as I mentioned, a co-program. And my department in particular, which is 90 plus faculty members with multiple research fellows, multiple fellows and centers and labs, and chairs, one of them. We have the following programs: computer, electrical, mechatronics, software, and nanotechnology. Computer and electrical are our programs, and we share the other 3. We are one of the first universities in the world to set up a nanotechnology program. And as I mentioned, it's a co-program. And within the grad program, these are all the groups that are basically carry out research. Now we are over well, right now I guess numbers have gone up a little bit, but we have about 270 or 300 PhD students, mostly focused on research. A group, the university, and I have 150 master's students. And we also have MH programs, which are basically programs by professional programs and multiple PDFs. These are the centers or labs in our department, and our group, my group, particular power engineering, focuses on the high voltage lab, which is one of the last high voltage labs left in good condition in North America, in Canada in particular. Now, the power group in general covers all these areas: power systems, distribution systems, markets, high voltage power electronics protection, and smart grids. And my focus in power systems is smart grids. So we're quite a varied group with 5 IEEE fellows, outstanding students, research, and multiple projects and contracts. And my particular group focuses on the following topics: smart grids, basically from the point of view of energy management systems for customers. We have developed a simulator and work quite significantly in the area of voltage optimization for industrial loads. So different aspects of active distribution networks. We work in renewable energy sources, from the point of view stability and control, modeling as well, and planning tools. And electric vehicles, we have done quite a bit of work in grid impact, looking at the impact of electric vehicles on the power grid, smart chargers, and distribution feeder control, interacting with electric vehicles. In microgrids, I'm going to be describing this in more detail, so I'll skip this. And we also do flexible AC transmission work. And recently, we have developed a new technology, a hybrid power flow controller, which we are basically trying to commercialize. And in the area, we also work significantly in the area of energy storage. Now, maybe I should, for the next description, I'm going to use my highlighter. Sorry. Lazy pointer. Okay. We in the area of energy storage, we do quite a bit of work on modeling and control. Okay, these are now going into the microgrid aspects of which is the focus of this presentation. These are the partners that we have worked with in this area, so multiple partners. I would highlight here NSERC, which is one of the main founders of this work, which is our Natural Science and Engineering Research Council. And also we have had significant support from NRCan, Natural Resources Canada, which is basically our energy Ministry of Energy. And we have worked with multiple partners, as you can see, including some academics, in part of some networks, and as well with communities, because in Canada, microgrids, as I will explain in a few minutes, are basically focused on northern communities, northern remote communities, indigenous communities. Now, going on to the outline of my presentation, I will be basically first giving you some research objectives of our work and definitions of microgrids, and then describe different aspects of the work we have done, focusing on energy management systems, stability analysis and modeling and control, optimal planning. I'll describe a lab that we have involved in near Waterloo, in Wells, Canadian Renewable Energy Lab, and then I'll talk briefly about our work in DC microgrids. So what are research objectives? There are threefold, basically. The first is all aspects of dynamic, static, and modeling, simulation, and analysis of microgrids. So we have done quite a bit of work in that area. Also, different aspects of optimal design, optimal planning, and consider basically focus on renewable energy sources, how to integrate them using local resources, and consider economic, technical, and social aspects in this work. And particularly focus on remote communities. Why? Because our work basically applied to Canada is one of the main focus in Canada in microgrids, as you'll see in a few minutes. The third aspect is all different aspects of control, dispatch and control, which I'll be describing. Now, what is a microgrid? My microgrid is basically a medium voltage, low voltage system, a feeder system in which you have radial systems, radial feeders connected at a very specific point to the grid, at point of common contact. And then you have a central controller that basically manages the different resources you have in the system, which include typically diesel generation, wind, solar, and it might include micro turbines and fuel cells, and certainly batteries nowadays, because that's the best way to integrating solar and wind. The microgrids that typically work with cover these different aspects: batteries, diesel, solar and wind, which is basically, and the controls of them, which is basically the resources to supply different types of loads. And you can have them grid connected or isolated. Now, from the point of view of control, you have 3 levels of control as per this task force Microgrid control, which I led. Microgrid control, which created this paper, which is highly cited, which basically describes all the different aspects of control and overview of the controls in microgrids. And basically, you have primary controls, then you have secondary controls, which is basically associated with the energy management system, and tertiary controls, which is basically the coordination of the microgrid with the grid and other microgrids. Now, in the area of energy management systems, we have worked with different aspects of energy management system. I'm going to describe briefly. First, we develop an unbalanced and decoupled model, which is basically described here in different blocks, and is described in detail in this paper. But basically, the idea is that you divide it like you do in a power grid. You divide the dispatch of the units you have in first unit commitment, and then which is basically a mixing interlinear programming problem, and then a non-linear basically model, the optimization, the OPF basically, which in this case is unbalanced, and you have a way of basically these two interacting so you have a feasible solution. And we use yeah, I'm getting a lot of noise here. I guess if you can, those not talking could be mute yourselves.
Can I
maybe the host can mute the
turn off your mics, please?
Huh?
You should be able to mute the people talking. Thank you.
Can I please turn off your mic, please?
Thank you. So the kind of techniques we use for considering uncertainty in the model, because you need to work with forecasts, it is a model predictive control, which we have designed a technique which is basically variable time steps to be able to manage the complexity and appropriately the forecasting horizons. Then we develop a coupled energy management system in which we merge the unit commitment and OPF, in which you end up with mixed integer non-linear programming problem, which nowadays there are tools to solve that type of problem, and included a smart load that basically interacts with this system, which is basically dispatched through this process. Okay, using again mixing model predictive control approach to account for uncertainty in the model. Okay? We also develop a model describing all these papers that I've been posting here, or by indicating here. I guess you'll have a copy of this presentation if you're interested. And it's basically a multi-objective microgrid model, in which basically you're looking at not only cost but also emissions, and different ways of introducing or mixing those type of different objectives, which can be contradictory, because emissions might be reducing emissions might end up costing you more. And then we have developed a model in which we integrate energy storage, but particularly thermal energy storage. This is very important in northern microgrids because they are cold climates. So if you have a furnace where you can store electricity, heat through basically turning on and off an electrical load, basically, that way you can optimally integrate or very integrate different type of renewables, which are intermittent. So this is a way which has been actually implemented in northern communities in Canada and the US, in Alaska in particular, in which you basically are able to store energy in form of thermal mechanism, as you can see here, to thermal bricks. Then we have worked out also all different aspects of thermal energy storage. We have worked in the integration of not only furnaces, but water tanks, CHP, different type of CHP, and also heat pumps. And then you have boilers. So you have basically a thermal system and an electrical system. And in this paper, we describe the modeling of the system and the energy management system to manage this system and this problem. And basically, we apply this to, which is a collaboration with the Polytechnico di Bari in which we apply this to a system where a microgrid they have developed, they have deployed in their facilities. And we have also integrated frequency into the problem, in which, because typically dispatch happens by intervals that you assume that this is basically remains fixed, whereas there's a frequency regulation that's happening between the dispatch intervals. So we introduce the modeling of these frequency response in the system in this paper to basically produce a better model of your system and have a better, more accurate dispatch model in your system. And then we have worked in practical aspects of BMS, because one of the important aspects of all of these, some of this has been integrated actually in a controller, is the dispatch models that we have developed, particularly the unit commitment. However, when you introduce these models, you do a lot of approximation. So we develop models and techniques to basically make these models as accurate as possible, but at the same point practical. It's basically, in the end, basically we linearize the problem, and you end up with a mixed intelligent quadratic programming problem can be solved very quickly. And it's described in the paper you see in front of us. And then we have worked in different aspects of including uncertainty in these models. The first one is the one I already described, which you can describe as wait and see, which is a deterministic problem model with a model predictive of residing horizon and residing horizon model. Okay, in which you basically track the forecast. You basically have you try to track the realization of the actual events with a forecast, and then you basically have reserves to compensate for these differences that you see. The next one is through a stochastic optimization described in this paper, in which you basically try to predict with probabilities how much likelihood that one of these events is happening. So you develop a series of scenarios and solve this whole problem, which becomes a very large problem then. That's one way of handling stochastic problem, one way of handling uncertainty. And other techniques we have developed, two particular techniques: robust optimization, which is basically a pessimistic problem, a view of the problem, in which you basically describe the uncertainties in terms of intervals. Okay? And another technique we have developed ourselves, a fine arithmetic, which is a technique we have developed in a lot of detail, in which you basically treat everything as intervals, the variables included, okay? As opposed to try to get to the worst condition or the worst dispatch possible, which is robust optimization, which is basic, very pessimistic. Whereas a fine arithmetic gives you both ranges, pessimistic and optimistic, in case you are a risk taker. And then in stability, we have done quite a bit of work describing all these papers. And in particular, we have recently generated, I guess as of last year, we have basically defined and classified stability microgrids, which was missing. And we have divided the microgrid stability in different blocks, similar to what has been done to power systems, which we have according to the characteristics of microgrid. And we won't get into the details because there's no time, but we have been able to define and classify all of this in this report, that you see here, and in this paper. Okay, where if you're interested in learning more about these details. And then we have developed different types of controls. One in particular that we have integrated in an actual controller is voltage frequency control, in which you basically take advantage in microgrids, because they're basically mostly residential loads. You take advantage of the fact that loads are, because there's no transformers between the load and the generation, no LTCs, I guess I have to be clear about that. There's no regulation at that level of the voltage is very low, if there is any. So through the regulation of the voltage in the grid, you can basically take advantage of regulate frequency. And basically you introduce this frequency basically control, a frequency loop that similar to a PSS, which basically regulates the voltage of your voltage sources in the system, okay? Which can be diesel generators, or you can have batteries as well. And basically what it's trying to do is, as you can see here, this is the result of wind variations, the frequency changes in the system. When you introduce this type of control, basically you almost behave like an energy storage. This is the energy storage, the dotted line, and the blue line, and the gray or the black line is what you accomplish with this type of control, which has its limitations because it depends on the limits on the system. But basically, what you are doing is effectively using the load as a dispatchable load, without affecting the load, which is very important. The load is not involved in this in terms of deciding to get involved, but you just regulate the voltage and indirectly you change the power. And then we have also applied thermal modules and energy storage to a microgrid in this paper presented here, in which basically what you do is use these thermal controllable loads in your system, water heaters, air conditioners, or ground heat pumps, one of the two, to basically regulate frequency. And you see the impact of, in this particular example of a microgrid in British Columbia, with a remote microgrid, in which you basically have a diesel generator and a lot of solar. And what you see is the impact of solar variations here. You can see that the frequency basically very significant. By using these resources, the thermal control loads, which have basically thermal storage, you can basically control the frequency and keep it within the boundaries, required boundaries for control. And we have also used frequency regulation, or an optimal frequency regulation approach, in which you basically, this is now fast dynamics, like in the previous case, in which you describe in this paper, which basically tries to regulate the frequency by basically optimally computing the droop, because that's one of the problems you have in microgrids, is that droop can make your system unstable, as you can see here. So by optimally controlling adaptively by these techniques, an optimization problem, you can basically make the system stable. And then we have applied, we have also working decentralized controls, including not only AC microgrids like this one, or through a back-to-back interface, but also for DC microgrids, also working through a voltage source converter interface, which is required. This is not actually required, so this would be an additional hardware that you would have to add to be able to coordinate optimally, or be able to have a proper behavior with microgrid. So we develop a series of controllers, as you can see here, that basically controls the DSC, whether it's a DC link, whether it's a DC microgrid and AC microgrid, to provide frequency regulation in a system like this. So when you have multiple microgrids, now you have a mix of AC and DC microgrids, and through these interfaces, which use voltage source, virtual synchronous generation interfaces, you're able to optimally regulate the frequency, which is what you see here. The frequency and the voltage in the DC microgrid. So you, from an unstable system, by applying these techniques that we have developed and these controls, you basically make the system stable. And now getting into we have also developed or participated in the development of a lab, a Canadian Renewable Energy Laboratory, which is described here, which is this center in which we basically have all located at Canadian Solar in Guelph, near Guadalupe, in which you basically have all these resources. So you have a PV array, a wind turbine, relatively small, but you also have PV simulators and wind simulators. You have diesel generation, and you have a large battery. The system has been developed in a way that the large battery, is able to basically supply all the loads, which are the controllable loads. Okay? And you also have a grid simulator. And basically, we have developed, we have participated on this effort, quite significant effort. And we have done some work in developing or applying our MS or developing an MS that works for that system. Now, from the point of optimal planning, we have done quite a bit of work, because it's quite relevant in the context of the Canadian node, as I'll show in a second, in which we try to basically optimally plan microgrids and determine what kind of, especially renewables, can be integrated into this system optimally. Okay? So we determine the most appropriate location, minimize the cost, considering all the constraints in the system. Okay? And this is the technique we have developed, described in these papers, in which you basically have a four-phase approach. The first one is basically identify all your resources, identify all the needs that you do have, then determine, forecast the renewables and the load, okay? And then basically pick, according to this forecast, determine the best, the data set for equipment for planning, because you cannot just use any available resources, any available equipment, hardware. So you limit the database or the data of the search space, and then you do an optimal an optimization which determines the number, type, and timing of renewable energy deployment system. We have applied these to microgrids in the Canadian North. And this is a picture of the Canadian microgrids, the northern Canadian microgrids, as you can see here, go from a few kilowatts to megawatts. Okay, so size doesn't determine a microgrid, but the characteristics of them, which I have described before. And these are the resources available in Canadian North in terms of wind and in terms of solar. Okay, which can be quite significant in the south, as you can see here, particularly solar. And wind is especially particularly available basically near water sources. And we have applied this to a community in Northern Ontario, which we have worked with, Casablanca Lake First Nation, which is basically located about 1,500 kilometers from Toronto, which is here, and 500 kilometers from the closest city, which is Thunder Bay. And there's no roads to access this. And these are the characteristics of the microgrid, which we basically instrumentalized, deployed all this equipment, basically meters from fast, very fast, milliseconds to seconds to minutes, okay, in houses, to basically have a full picture of what happens in these microgrids. And that gives a very good idea of what the characteristics of microgrids are, which are unbalanced. The grid doesn't play a major role, so voltage regulation can be done through the main sources, the generators, basically. And the third characteristic is that basically frequency can be very much affected by a variable generation, solar and wind, particularly wind in the north. And we have applied these concepts as well for these communities in the Northwest territories and the Nunavut territories as well, Nunavut province. And finally, to finish my talk within the 30 minutes that we have set, 35 minutes, I guess. We have done quite a bit of work, or recently have done significant work in these microgrids. Besides the controls that I already described, or the techniques we already described, I already described before, models and techniques. We have basically developed an energy management system described in this paper. And a DC microgrid basically is a grid in which you basically, everything is DC, okay? And I'll give you an example in a second. And you need to develop models and controls for those different systems. And the characteristics of these microgrids is that you have voltage sources connected through DC-DC back-boost converters, okay, which basically allows you to regulate the voltage. So in this case, you don't have frequency problems, you have voltage problems, okay? But the characteristic of these, the problem with that is that now you don't have a signal that you can rely on throughout the system. Frequency allows you to basically know what is happening in your system across the system. Voltage doesn't have that characteristic, okay? And then you do have less losses. And the other problem you have in these microgrids is that you don't have zero crossing, which creates a lot of protection challenges, particularly from the point of view of breakers. Now, mostly you find it nowadays in buildings. That's where you have these microgrids, but they are evolving in a sense that are being deployed more widely. Okay? And this is the lab we have worked with the Chinese colleagues. A lab in which basically is a DC microgrid already in that building, in which you have 380 volts, and then you have a battery, which is the main source. You have solar panels, significant solar panels, and then you have basically lighting load, electric vehicle charging, and air conditioning, which basically is an AC load. So you have an AC-DC interface, a DC-NC interface, and then you have the connection to the grid. And we develop a model considering battery degradation, okay, which is basically an EMS system in which you have these inputs. You have the PV inputs, the electric vehicle charging, the LED lighting, the AC charging, and then the electricity cost. And with that, we develop, because this is a multi-objective, by the way, optimization problem, we develop basically a dispatch, depending on how you play with these variables out, okay, with this multi-objective optimization approach. So depending whether you give more weight to the gradation or more weight to grid cost, you have different types of dispatches, which is what is reflected here. And finally, to finish my talk, we have done work in DC microgrid power flows, okay, which is described in this paper. And then you basically have a model of a DC grid with different sources, which can be AC or DC. and a balance, okay? And then you basically develop a model, a linear model, as you can see, a circuit model of that system, and apply, and in this particular case, apply all these different type of solvers, power flow solvers for this problem. And we developed two new methods, briefly mentioned here, and which we compare in a relatively good sized microgrid, which we generated. We developed this test system and see what the impact of that system, depending on the characteristics of the PV, the household demand, and the electric vehicle. So based on a 24-hour window, we were able to compare them in terms of how much, how fast they can solve the problem, how accurate the problem is, okay, and got a good sense of how this works. Okay, that's my presentation. So I welcome any questions that you may have within the allotted time.
Thank you, Professor
Thank you,
Canizares.
sir, for your excellent speech.
Thank you.
It is really very scholarly and mesmerizing. Participants have definitely learned a lot from you from this session. Now, if you have any questions, I would request you to raise your hand. If you have any questions, please raise your hand.
I do have one question. Okay.
Yeah, please go ahead.
Thank you, Professor Canizares. This is Professor Abdullah. Thank you very much for responding positively to talk in STI 2020. I do have one concern related to optimal uses of NRC. Professor Claudio Canizares, you know, in Bangladesh very recently, the amount of NRC that is producing has been increased significantly, but still we are very poor in efficiently managing the energy resources. I mean, a very good amount of energy is being under wastage category. So how can we effectively utilize the concept and the technologies related to smart grid so that we can monitor the actual requirement in a certain time, that is real-time monitoring of the requirement, and based on that we can provide the supply. You can supply the energy amount from the power distribution companies. So this is one of the important concern in efficient utilization of the energy resources that we are producing. So that's my concern. Thank you very much.
Sure. What do you mean with NRC?
I mean, basically, I'm talking about the
Renewable
power that
energy
we are
sources.
producing need to be utilized efficiently.
Okay, you are not talking about renewable energy sources.
No.
Or
That
in
is
general.
the total power that is general power.
Okay,
that
well,
is
I guess my talk wasn't focused on that. But however, I guess I can give my opinion, the work we have done. But I'm not quite sure what the problematic in Bangladesh is, so can't really comment much on it. But for example, in Canada, what I can tell you is that what is happening is that there's more focus in integrating renewable energy sources. In that context, I guess the problems that we face are somewhat different to what you do, because we assume that we already have a fairly stable system, right? A well-managed system with enough generation resources. The problems that are happening, or what has been determined, is that you need more flexibility on the load. Okay. Not only because of renewables, but because that would allow you to basically reduce costs and defer investments, because there are congestion problems. But however, these become particularly important when you have renewables, because when you have renewables, they create a lot of variations in frequency in your system, and that which is what I was telling you the same story that you have in the microgrids. Although microgrids is more critical, in larger systems you have more inertia, more resources that you can play with. However, the more renewables you introduce, the more you get closer to what a microgrid looks like in terms of very fast frequency variations. So in that context, load resources which requires that you have basically, you can see the load, that the loads can respond and communicate, which is basically the essence of the smart grids. Smart grids, I mean, at the transmission system level already exist. They've always been smart. You always had control communications of generators. What you didn't have is load involved in the dispatch problem, involved in the control problem, which is the essence of microgrids. Pardon me, smart grids. And in that context, I guess we're talking about medium voltage, low voltage networks, which now become part of basically the control and the dispatch process. And if you add to that generation at that level, then you have an active network, which is able to basically, or should be able to interact with the upstream network, the transmission system network. And that creates a whole bunch of challenges, which are basically the focus of a lot of research papers nowadays, and of interest to utilities. Hopefully that addresses your question.
Thank you, Professor Canizares. I believe there might be some other questions. Yeah.
Professor Canizares, as session chair, I have an apology. Since we are behind the schedule. In fact, I got my online class for the BUET student exactly at 11. So I have to quit. I would just request Professor Q. Hassan, Kamrul Hassan of Green University, just to be the session chair, okay? Because I have to quit this, because I have to be connected virtually to my students at 11 o'clock. Thanks a lot to you. I think our audience and in general, they have benefited from this, and they can also email, or they can have through other virtual platform, they can be connected with Professor Canizares for his nice topic, which is, these are the timely topics. Okay, these microgrids especially. Of course, microgrids enabled by this. It's due to promoting to promote the renewables, and microgrid, of course, it needs both. I mean, what it's called this renewable as well as non-renewable also, because only renewable, I think, unless you go for load shed, okay, it cannot. I think if
well, you have batteries, you can do it, yeah.
Yeah,
you
yeah.
have renewable systems, yeah.
Yeah. So we need also both, I think. Am I right, Professor Canizares? I mean, we need both conventional and this renewable also for microgrid. So anyway, so I think it was a nice topic. So I have an apology because I have to quit it. So thanks a lot. I think Professor Q. Hassan can conduct the remaining session. No problem. Thank you very much, Professor Canizares.
Okay. Sure.
Thank you, sir. Do you have any other question, please?
Well, I have a question. Professor Canizares, I have a small question regarding if you have a DC and AC microgrids interconnected. In that case, in AC system, the main control variable is the frequency. However, in the DC system, I guess the voltage is the control variable. Is there any other control variable in the DC microgrid system? Let me ask you a second question. I have seen that you have, for your solar panels, you have solar irradiation forecasting. But for your wind turbines, do you also forecast the wind velocity as well?
Okay, so let me see if I got the first question. In the case of AC grids, basically you have two parameters to worry about: frequency and voltage. And frequency is challenging to control. It's the most challenging problem in AC microgrids. Frequency. Try to regulate the frequency, especially when you have renewables, because as you mentioned, you need to forecast solar and wind, and that's not easy. That especially when you are doing it at a small regional, very local areas, because that's where microgrids reside. So it's hard to do. So this variability creates a lot of problems, okay? And that basically creates frequency problems. When voltage is not as much of an issue in terms of, as long as you have the resources, it's not much of an issue in AC microgrids. In DC microgrids, which is the picture, basically this is what we were playing here with. In DC microgrids, you only have voltage, okay? And voltage is the main source of regulation. Of course, you try to regulate current to basically dispatch power, but the main concern is voltage. And the problem with voltage is that is not a common signal, so it changes throughout the grid. Okay, whereas frequency can be seen practically the same in one point or at two extremes of the grid. So that creates a lot of communication issues. So that's an additional challenge you have in DC microgrids, which is the communication level. Basically, you have a cyber physical system that creates a lot of challenges. Now, regarding the forecasting issues, yes, you need to have a forecasting tool. If you are dispatching, you certainly need to have that. And that's one of the prompts that generates the prompts of uncertainty and how to integrate them into the dispatch prompt, which is basically a different type of modeling or using model predictive control, which is what you actually do in practice. Try to basically look ahead, predict what the forecast is going to be, and then with that forecast, try to determine what your dispatch is going to be. And then you keep doing it every 5 minutes or every 15 minutes. Hopefully that answers your questions.
Thank you, sir. I hope we have learned a lot from your session, sir. Thank you for your kind presence today. Now I request the moderator and acting session chair of this session, Professor Dr. Kamrul Hassan, to confer the vote of thanks to the respected keynote speaker of this session.
Bismillahirrahmanirrahim. I begin with the name of Almighty Allah, who is the creator of the universes and who is very kind and continuously merciful. Assalamu alaikum. Peace be upon every one of you who is connected to this keynote session room. On behalf of the conference, STI 4.0 committee, the Green University of Bangladesh, and of myself, I congratulate Dr. Canizares, the professor of University of Waterloo, Canada, a fellow of IEEE, the largest professional body in the world, for his wonderful speech on microgrid. The overview presents all the aspects of microgrid planning, operation, and control, and also the problems with the renewable resources and to some extent the dependable and diesel dependency. One beautiful thing of this lecture is that it provides the audience the research outcome on the first-hand collected data of a remote community of Canada. I'm really thankful to Professor Canizares. On behalf of this conference committee, the Green University of Bangladesh, and myself, I'm thankful to Dr. Sahanaz Ahmed, who is the professor of Bangladesh University of Engineering and Technology. He is a well-known academician and researcher in power system, particularly smart grids. Now, as a token of appreciation, I like to confer a certificate to the Renewable Session Chair, Professor Sahanaz Ahmed.
Hello.
Can you please put off your microphone? So,
Dr. Jagannath, please mute your microphone. Okay, sir, done. Thank you.
Okay,
Thank
we
you, sir. Now,
congratulate Professor Sahanaz Ahmed with this, and this is a token of appreciation from our committee. Then I request Rapporteur to confer a certificate to the distinguished keynote speaker, Professor Canizares.
Well, thank you very much. Thanks for the invitation. It's been a pleasure to be here. I guess I'll pass on the slides so you can, if you're interested, you can peruse them, and if you have any questions, I'll be happy to address them. Thank you very much. Thanks for the invitation. Thanks
Thank
for
you,
the
sir.
certificate.
Thank you, sir. We'll be ever grateful for your kind presence and valuable input. Now, with the kind permission of Honorable Session Chair, I would like to end this session.
Okay, thank you very much, Dr. Atil, Professor Kamrul Hassan, and Professor Sahanaz for being connected with us to facilitate this keynote session. I deeply express my gratitude to Professor Dr. Claudio Canizares for responding to our call and give a very valuable talk for our young scientist and author. Professor Claudio, thank you very much. And we do have a very good connectivity in future days. So thank you very much again.
Thank you. Thanks. Have a good conference. Take care.
Thank you.
Thank
Bye
you
now.
all.
Bye now.
Okay, so we do have amongst us the next keynote speaker, Professor Vincent Tong. Professor Vincent Tong, can you hear me?
Yeah, I can hear you.
Yes, thank you very much.